Hey, everybody. I hope you had a good weekend. Let's resume our lecture. So before I resume my lecture about the trio, background FSCK snapshot and the soft update, I would like to make I think it's a very important announcement. Um, I already made up the question for your midterm, number one. Um, And I realized that this particular lecture is very important for preparing for that midterm. So I'm just give you a hint that uh, a large part of to answer the homework assignment, not homework, midterm number one is actually in today's lecture. Okay, just let you know. This will be recorded as usual. So if you miss anything, you don't understand anything, we can always cover that through office hour discussion. Okay. All right. So I'm going to share my screen. Okay. So a lot of things we're talking about this few lecture is all related to reliability or crash recovery of a file system. As you can imagine that if I have a machine that my CPU occasionally will crash, that's one thing. But if I have a machine which the file system crashed in a bad way that actually I no longer can use the file system, I lost file. That's actually much, much more serious. Because if you have any like a software crash or operating system bug, I mean, it's not ideal. With fault tolerant computing, sometimes we can handle that, especially the modern system design. We use a lot of redundancy to recover. But you know, you have a way to recover. But for file, for your data, if you lost it, I mean, later when we talk about Google File System, GFS, you will see that they actually have a redundancy also in a distributed sense. That's actually for the main topic for the second midterm. But for a single processor file system or single machine file system, then we are really need to make sure we design the system such that regardless how you crash, regardless when you crash, we will be able to maintain a file system that's recoverable. At least majority of your data is still basically protected, and then you can continue to use it as much as possible. So we talk about both the availability of the data, and also we talk about how fast you can use that availability. That's both very important. Okay. So last time we talked about soft update, the third topic of the trio. And then we talk about it's important to decide when you have a bunch of disk block that you need to write back from your dirty buffer to your hard disk. And the thing is that the rule in front of us, this three rule in front of the screen, basically say you need to determine the order about which block you need to write back. For example, the first rule say, never point to a structure before it has been initialized. So for example, if you have a directory block, which has a pointer to inode block, so now the pointer is from the directory block to the inode. So that structure is the inode. So essentially, if you have a two block, one is inode, one is directory block, then you need to first write the inode, which is the structure, to the hard disk. And then you write the directory block, which is a pointer. So this is basically the first rule saying that for the creation, you have to write inode first and then write directory block, this too. Well, in deletion is opposite, in fact, because you want to, the second rule is that you don't reuse a resource before nullifying all the previous pointer. So in that case, you want to nullify the pointer. That means you want to write the directory block first, and then you write the inode block. So this is basically the rule that imagine you have a situation, we delay all the write back to the hard disk, and you have a bunch of dirty memory blocks, and you want to write back according to the order specified by this 3 rule. And it's very important that you want to design it in a way such that regardless how, when it crashes, for example, you write 1 block or write half of the block, it crashes. I mean, how do you actually make sure that you've done the right thing and such that even that kind of unexpected situation, your file system still will maintain this property? I actually put down in the slide that this is the property that we want to maintain, which is, if you forget anything else, is basically L has to be greater than or equal than D, which means that if D greater than L, we're in big trouble, as we point out. And the other thing is between the pointer block and the free block bitmap, which they cannot be 1, 1. It could be 0, 0, or normal, it should be 1, 0, 0, 1. But 0, 0 is okay. We just need garbage collection. But the thing is that you cannot have a 1, 1. If you have a 1, 1, we're in trouble. So essentially, if you remember the logical circuit design about how you can transition between two variable, Boolean variable, in order to avoid this kind of hazard condition. So we always go this way. If you think about this, is always, if you want to go from 1, 0 to 0, 1, 1, 0, first go to 0, 0, and then go to 0, 1. Or if you want to go to 0, 1 to 1, 0, you first go to 0, 0, and then go to 1, 0. So that's the transition. Each of the transition represent the order of the block you want to write back to the hard disk. Okay, so that is what we have talked about. It's a very complicated scheme, especially if you look at the program. If you have the textbook of FreeBSD, you will see that the data structure for them to keep the sub-update is fairly complicated. But the principle they are essentially try to implement is in this slide. Is basically, how do you guarantee L greater than, always, regardless, L always greater than D, greater than equal than D, and also you make sure that between these two pointer block and the free block bitmap, you cannot have a 1, 1. Okay, that's the 2 condition. If you guarantee, then essentially soft update accomplish his purpose. Then basically snapshot and background FSCK will took care of the rest of the stuff. Okay. All right. Now I'm going to move to probably the most interesting case. Okay, so essentially we have some delay write, means that you have done a bunch of things to your file system and you never write back to the hard disk. And the 2 block in front of us is basically in the memory. Okay, we have 2 block A and block B. Block A is a directory block, block B is a inode block. And the thing is that the yellow represent the foo and the inode2, they are in a pair. Okay, so foo is a directory entry that has a pointer to inode2. And the thing is that we're going to delete this. So essentially, the yellow represent this particular file, foo, is being deleted in the memory. It's not in the hard disk yet. And then we have another transaction. It just happened. They also involve exactly the same 2 block. So the blue is actually create a file called bar. So blue is creating a file, which involve bar and ino3, and foo is deletion, which is involve block A as a directory entry and block B as ino. Okay, so now we have this two. So now I want to ask you a question. If I have this 230 block, I want to write back to the hard disk. Which one should I write back first? Okay, what I want you to do is that I'm going to put you into different breakout room, about maybe 5 student, a breakout room. And I want you to just talk about this to see, you will decide based on what you learned about soft update. You're going to discuss which block you think you should be right back to the hard disk first. Okay, when I want to do this synchronization, let me actually put you in. Okay, let me see. I have.
Excuse me, Professor, I have a question.
Yes, go ahead.
So what are we supposed to discuss again before we start?
Okay, let me share my screen again. All right, just give me a second. Hey, Angela, this is what I meant. Okay, you have 2 block in the memory. Those are the dirty blocks. So means that in the memory, my application program already done 2 things. One is to delete a file called foo. One is called create a new file called bar. All right. So when you have a deletion and creation, I'm actually going to have a 2 dirty block in my memory. Block A is a directory block, which with that yellow and blue. And block B is the dirty block for ino block. It's an ino block. So the yellow really means that foo is no longer there. And similar for block B, the yellow ino2 means ino B2 will be wiped out without anything. So you will only have a 2 block looks like this. So my question for you is that now I'm going to write my dirty block back to the hard disk, which is going to make it permanent, make those changes permanent. So the thing is that this is a sequential writing. I can only write 1 block at a time. Which block I'm going to write? Block A first or block B first? That's my question. Is that clear?
Yes, thank you.
Okay, you're welcome. Okay, I will give you 5 minutes to talk about this, okay?
Hi, Professor. I just joined in real quick, so I had to come back from an interview. Could you just update me real quick?
I will assign you to a group. Don't worry.
Oh,
thank you.
Okay. All right. Thank you.
Yeah, thank you. Hey, Franklin, are you here? Hey, Franklin. Okay. Okay, let's continue with okay, so regarding this two block, wait a minute, I need to get to full screen. Okay. Regarding this two block, so based on your discussion, which block should I write back to the hard disk first? Block A or block B? Anybody? I didn't hear anything either in voice or in the chat.
Professor, I think it wouldn't be straightforward because if we will write any one of them, it will violate the condition either for deletion or creation.
Right, that's very good. So I kind of trick you, right? It's actually a circular dependency because based on the rule for creation, it's going to be block B first, and then you're going to write block A. So if it's creation, I'm going to write I know block first and then write directory block. But based on deletion, I'm going to write block A back first and then block B. So essentially, in the soft update, I'm maintaining a dependency graph. Looks like this, but usually much more complicated. And the thing is that if you actually learn the algorithm class, is saying that, well, can you actually write a code to detect whether there is a cycle in a graph? Here is application that you actually need to go through the dependency graph and check whether there is indeed there is a loop. If there is a loop, then you know you are in trouble. You actually have a circular dependency. We need to do something about it. So let me actually give you an example and let me give you a concept. The concept we need to do is that we have to break the loop first. So in order for us to write both block, or maybe the loop is not just 2 block, it might be 3 block, 4 block. So if you look at the sample midterm, it actually is a loop involving 4 different blocks. That's actually how you're going to break it. So when you found a circle, then essentially you try to break it. Once you break it, no longer have a loop, then you can apply whatever the rule we have before. So now I'm going to show you how to play the trick for you to actually break the loop. So I'm going to use this example. So this example, you can see that I have a block which is similar to the example I show you. You can see that over here I have a INO block, and over here I have a directory block, and this is essentially what I have in my memory. And so here are two other blocks, which is the same block, but they're actually in hard disk. So think about this. In any file system, you're going to have a multiple copy in different position in the memory hierarchy. And the thing is that the main memory represents the current status. This is the place we really want the file system to be. And we need to synchronize this to the hard disk. So you can see, let's actually compare the blue rectangle and the red rectangle for the top row only. So you can see that, let's look at the difference between this INO block and this INO block. So just tell you the convention, if it's a gray, that means that this block is actually, this INO is actually free. So essentially between these two is that INO number 4 is the new file that's being created. So INO number 4 is created, also directory entry A, which has a pointer to INO number 4, has been created in the memory. And you can see that in the hard disk, neither of this were there. That means that because this is file being created, but the file being created only in the memory, not in the hard disk. By the way, there is a Unix command called sync, S-Y-N-C. When you actually type the command sync, it will force the program to actually syncing with a hard disk. That's the command supposed to do. Okay, so let's look at this. This file A has been created, but it's only created in the main memory. It's not in the hard disk yet. And then there is another difference, which is INO number 5 has already become gray, and then the file B is gone. This entry, this directory entry is gone. But if you compare what's have in the hard disk, you see that there is an INO number 5 is active there. And then there is a directory entry, which is the B pointing to INO number 5. So essentially, this is a deletion already happening in the memory and not yet in the hard disk. So essentially, what we have in this situation is a circular dependency exactly match what you actually discussed just a couple minutes ago, okay? But our goal, I want to move this a little bit up. Our goal is that we will be right back the hard disk block, right back the dirty buffer back to the, back to the hard disk, such that eventually I will reach this state. In the bottom of this figure, you can see that now whatever you have in your memory regarding this two block is exactly the same as the one in the hard disk. So we want to do the synchronization or sync in a way such that eventually both content will be actually put in here. And in the whole process, while we're doing that, we make sure that even if your system crash, you're not going to see D greater than L. You're not going to see 1, 1 in that case, okay? So that's what we're going to do. So now you can see, if you look at the space I have in the middle, you can see that, let me move these things here. You can see that there is actually 2 rows, okay? There are 2 rows of blocks I'm going to show you in a couple of minutes, but I just want to tell you, here is a high-level idea. If you have 2 blocks, you're going to write back to the hard disk. How many blocks I need to write back? 2. I suppose to just need 2 blocks, write back to the hard disk, I'm done. But just look at this. Let me actually show you the answer so you will actually know what's happening. So this is the solution. really want to get rid of this. Let me just move it here, okay? So you can see that. Let me actually tell you the solution, and then we'll see what's going on here. So each of the row represent one block written back to the hard disk. So this was your original state over here. And now we're going to compare, just focus on the first row and the second row. The first row to the second row, you can see that the difference. Now we're looking at the hard disk part, because memory, you can see that the memory is unchanged. I never changed the memory. It's actually the most current one. But look at the hard disk. The first block I roll back is directory block. I actually roll back, it's a directory block, but the block of the directory block I roll back is not exactly as the directory block in the memory. So just let you know, I will explain why is that. Okay, so I'm actually write directory block once. You can see that over here, I didn't change. If you vertically, you change between row 1 and row 2. I didn't write inode block. I only write directory block. Okay, now let's actually compare row 2 and row 3. Between row 2 and row 3, you see that directory block has remained the same. Now I write the inode block. I write this inode block into here. So now you can see that I'm actually getting this state. Now I'm actually looking at the last one, which is the row 3 and row 4, which the inode block is the same. So meaning I'm actually writing the directory block. Now this directory block is exactly the same as this. So the trick here is just make sure you completely understand this part. If I have a too dirty block, I'm supposed to just write 2 blocks to the hard disk. But in this scenario, I actually wrote 3 blocks. I wrote directory block twice. First time from row 1 to row 2, I write directory block once. And from row 3 to row 4, I write another time directory block. So I write twice the directory block. I roll inode block once. So essentially what I'm doing is that the magic is really happen in the first, the magic really happened in the first block. I want to move, see, they need to help me to design this the Zoom control bar. It's always blocking into my slide. Anyway, so the trick is the first write. The first write, essentially, I'm actually writing from the directory block to this directory block. All right. So so this content I roll back is not exactly the directory block. It's not exactly the direct block in the memory. Obviously, it's not the directory block here. So this one, I want to tell you the trick is that this one, I'm actually doing what I call rollback. So I essentially, because now I have in my directory block, I have 2 transactions. One is deletion, one is creation. And this 2, if both the impact or effect of that deletion or creation were there, then I'm actually going to have a circular dependency. So therefore, I need to roll back one of them. I roll back one of them and such that I actually get a block which has only, in this case, I only has the impact of deletion. Let me see. Yes, I only have the impact of deletion and I roll back the creation. I roll back the creation. So essentially what I did here, you can see that A, remember, item number 4 and A is the creation. So I take the directory block and roll back the creation to come out with this block. And then I write it back here. So when I did that, essentially I break the circular dependency because now I actually already fulfill the one. Once I done this, you can see that one of this basically dependency is gone. And therefore, I will be able to continue without any dependency. Okay, so let me summarize very quickly what I did. In order to break the circular dependency, I have to waste one more disk block write. Instead of 2, I have to do 3. And for that extra one, which is the first one, in order for me to break the circular dependency, I have to roll back one of the operation that's causing the conflict. And then once I've done that, the rest of them is straightforward. Okay. Any question?
I have a question.
Go ahead. Go ahead, Sai.
In this scenario, after step A, the number of directory blocks is less than inode blocks, which is what we are trying to.
Exactly. Exactly. So when you do this, if the machine crash, L is going to be greater than D actually, because you see that your D is actually less.
Yeah, so that's why you did this. Okay,
right.
That makes sense.
Right.
So always deletion takes precedence. I mean, so fundamentally, what we are trying to do is just ensure that your D is greater than N.
Right.
To break.
That's true. But you actually asked a very interesting question. I want to ask this question. So I'm saying that I can roll back, right? I can roll back in this case, I roll back a creation, right?
Correct.
But can I roll back deletion and then write back the inode first? I can write, the reason is I roll back creation, so I write the directory block first. But can I roll back the deletion and then write back the inode block first? Can I do that? It's a very tricky question, but I want you to think about this.
But if you do that, I think then L will be greater than.
No, if you do it that way, L will be still
less.
greater than D. Yeah, because I'm going to roll back. I'm going to write inode block first. I'm not going to, if I roll back deletion, I'm going to write the inode block. I'm not going to write the directory block. You see, I roll back creation, so I write back the directory block first. But if I roll back the deletion, I'm going to write back the inode block first. So it's supposed to be symmetric. I can break the dependency of the creation, or I can first break the dependency of the deletion. Either way, it's in theory, they're actually the same. But this is a tricky question. I want you to make sure you understand. But we always roll back creation. In the engineering design, we don't roll back deletion. Remember, when you talk about rollback, you have to think about what information you have is in the memory, right? If I roll back a creation, what's the rollback creation? Think about this compared to this block in the directory block and this directory block. This is the rollback of a creation, right? So if I roll back a creation, that means what is the value I'm roll back into? It's a blank, right? So when you roll back creation, what's before creation is a blank. So I can always roll back to creation, no problem, because I know it's a blank. But rollback deletion has a problem. If I want to roll back deletion, this is my memory. I want to roll back the inode number 5. So rollback deletion means that I have to recover the inode number 5 here. Guess what? In the memory, what's the original value of inode number 5? It's already gone. It's being erased, and I don't know what that value is. It's not blank, I know, but I don't know what that is. The only things I can retrieve that value is actually go to my hard disk to retrieve inode number 5. That's the only copy I have for the inode number 5. So essentially, when you want to roll back deletion, it's actually going to cause extra performance problem because you're going to access the hard disk again. So that's why we always roll back creation. Rollback creation, I don't have to remember what's the old value of that because that value is blank. but rollback creation, I'm in trouble. Okay, rollback deletion, I'm in more issue I need to deal with. Okay, so this is the way I'm going to actually skip this part because I really want to get to the next part today.
Professor, I had a question.
Yes, please.
So with respect to the steps of the updates, it would first go, correct me if I'm wrong, so first the directory is updated for the deleted file, and then it would update the inode for the deleted file, then the inode for the created file, then the directory for the created file, correct?
Right. Yes.
Okay.
So this is basically right. You see that this was old copy. The first one, the third one, you actually write the inode block, and then you write the directory block. Over here, yes, this is a rollback version of the directory block. Yeah, you're right. Does that answer your question?
Yeah, it does. Thank you.
You're welcome. Okay, here is a summarization about what we talk about. Is essentially you want to make sure you got a rollback, and then you actually write it back to the hard disk. Then you roll forward. You actually recover that because after you roll back, okay. By the way, there is a one small detail I didn't mention, but it's important is when you roll back, you have to keep the value before you do the rollback, so you can actually perform the extra block. Okay, so essentially you have to break the dependency, but now you have to write twice for the block A, which is the directory block. Okay. Okay, I'm going to move. Oh, by the way, this is just a data structure for maintaining all the dependency relationship. I'm not asking you to look at this, but just give you a feeling that it's actually quite complicated to manage the data structure to detect the circular dependency. Okay. Okay, I'm actually going to just hopefully you got an idea about soft update, about what property is actually guarantee of the file system. Basically, it's a 1-1 and D is greater, it's guaranteed you will not have a 1-1 and D greater than L. So I'm going to talk about the next subject, which is journaling. So journaling is try to do the same thing like what soft update is doing. And the journaling file system is used by most of the Linux operating system. So I'm going to explain to you what is journaling, and then I want you to discuss what's the difference. Do you think which one is better between the journaling and the soft update? All right, this part is very important. So journaling is using a concept called write-ahead logging. It's called write-ahead logging, and then I will explain to you what do I mean by that. I'm going to directly using this figure. Okay, so essentially what you have is that this is your file system. This is your file system, which is, I mean, it's the same thing. I have what I call 30 pages, and I want to write back to my file system. Okay, now just to let you know, the left-hand side is your hard disk, permanent file system. Your right-hand side is your memory. So here's what journaling will do is that the red part represent all the 30 pages that currently you accumulate in your file system. So I accumulate a bunch of things. I call it a log. So this red part, including a bunch of this, you can consider maybe for our example, this will actually include both the inode page and inode block and the directory block. So you can think about right now, the red part contain those two new pages that we just talked about in row number 1 in the example that I want you to discuss earlier. So now here is the journaling. The journaling is a concept. This is that, okay, in order for me to maintain the file system is consistent, I want to make sure that either both those 30 blocks got written to my hard disk, or none of them actually got written back to the file system. So this is a concept almost like a transaction, which we will talk about transaction concept later, is either all or nothing. You don't have like, oh, I only write one block and then the other block doesn't happen. No, it doesn't worry about like a circular dependency kind of situation. It basically say, hey, either I write both or nothing. That's the idea of journaling. Okay, so red represent the log or the journal of a journaling file system. So this is the 30 page. So the way it works is this. In the journaling file system, when you write back, you do not write the whole thing back to the yellow part, which is your file system. The real file system is actually the yellow part. But in the journaling file system, there is another area called log area. So essentially what I did is that I actually, if I'm going to write back, I first need to write the whole log, which contain multiple 30 pages, to this red area first. So I'm going to write it over there. And after I'm done writing every single pages to the red area, then I move to my second step called writing to the real file system. Then I write every single block from the red in the hard disk to the yellow. And upon I finish every single block, right back to the yellow, then I'm going to remove the red. So now the 30 log is gone. So let me actually just summarize what I said. When you actually modify the file system, you actually accumulate in the red, which we call that your log. And when you actually try to synchronize your memory with your hard disk file system, you first write every single pages to the log area of the journaling file system, which is the red in the hard disk. Upon completion of that, then you start to write everything from the red to the yellow. And upon completion of that, you remove the red from the hard disk. And that's the journaling file system. And why this will work, if you think about when the system can break, the system can be shut down or broken or crash. There are at least two different periods of time. The first period of time is that in the process, when you actually write from the red in the memory to the red in the hard disk. During this time, you haven't completely written the log in the hard disk and the system crash. So in that case, when the system get turned on again, it actually see a log entry that's actually half cooked. It's not being completed. When you reboot the system, they just get rid of that incomplete log. And if it's get rid of that incomplete log, then basically nothing will happen. Remember, the purpose is all or nothing. So if you haven't been able to completely written the red log, then essentially nothing will happen. All of this update will be lost, essentially. Okay, that's the first case the system could crash. The second case system could crash is that you already complete the red log, and then you actually started. Remember I said once you complete, I will put a mark, say, hey, this one is complete log, and then I start to write it to the yellow, write it to the real file system. And in the middle of that, I haven't finished that, and then the system crash. So when I reboot, I actually will see, hey, wait a minute, I actually see a complete log here in the file system hard disk. And it's there because I know if I already finished everything in the log to the yellow, to the file system, I should have removed that red thing. But the red is still there. That means I probably haven't finished. Maybe I finished 1%, maybe I finished 99.5%, but I know I'm not finishing 100%. As long as I'm not finishing 100%, I'm going to rewrite this whatever page I have to the yellow again. So essentially, I'm going to rewrite. Maybe you already done just 1%, or maybe you have done 99%. Doesn't matter. I'm going to write the whole thing. A pound is finished, then I'm going to remove this. Okay, that's called journaling. The thing is that every block need to be write twice, because the first you need to write to the hard disk, the log area first, and then you're going to write to the yellow. So it's basically there are two write if you have any file system crash in this case. Okay. Any question about journaling? Okay, so
Sir, I have a
this is
question.
basically the system design. I mean, the question asks how often you're going to do this. So there is a parameter. For example, you do it every cycle of some kind of activity, or you do it whenever the I/O channel or CPU is free for you to do that. In between those, that's kind of configurable. Okay, any
Sir,
other
I have a-
question about journaling?
I have a question.
Sure. Can you speak up a little bit? I kind of barely hear you.
Yeah, does that journal also store what data to write or just what when?
Okay. Journaling, we store both metadata as well as the data itself. So essentially, it store you could put anything. You could put data block, directory block, inode block, pointer block. You can put all of that in the log. And just to let you know, the way journaling really accomplished is all or nothing, means that I don't need to worry about dependency at all, because the way it works is that I always write everything back. So I kind of miss that criticalness in the soft update that I have to decide which block I'm going to write first. Because if I actually, I mean, the earlier the student asked an excellent question about how frequent I should do that. As long as you make sure your log is not accumulate so huge, then essentially this actually gives you some advantage about the simplicity of the design, and I accomplish all or nothing in this case.
Thank you, Professor.
You're welcome. Any other question about journaling? Okay, so I'm actually going to ask you a question then. How do you actually compare journaling and soft update? This is two different approach. Journaling is actually for Linux, which it will actually introduce some extra disk write all the time. But the design is simpler. And soft update, you can actually recover some partial result. But the thing is that there is a software complexity, as I showed you earlier. Okay, so this is important. I'm going to ask you to discuss this next question. I want you to actually compare soft update and journaling in your breakout room. I'm going to put you back to the breakout room in just a second. But I want you to think about the third bullet here, is that any design of the system will be suitable for certain application scenario. I want you to think about in what kind of application scenario that one of the idea, either soft update or journaling, will be superior than the other one. Essentially, I want you to think about what are the requirements that driven by the application, or what type of application that's going to be for us to make a decision whether I should go for soft update or I should go for journaling. Okay. Is my question clear about what I want you to do? Discuss about under what situation, driven by application requirement. I want to emphasize that. What kind you have to come up with your own application. Like this application, is this doing PowerPoint presentation or doing Zoom or doing whatever application that you think that for a file system. I mean, of course, when we talk about this comparison, we think about things will crash anytime. And whether soft update is better in terms of recovery or journaling is better in recovery. Okay, I'm going to now put you back to the Zoom. So now Zoom, put it back to the breakout room. Okay, you got about 5 minutes, all right? Okay, I hope some of the group, let me see, we're waiting for another 28 seconds for everybody to come back. Okay, I'm looking for a volunteer among ourselves to share with the rest of us what's your thoughts regarding the question. Under what situation you think that soft update is preferred? Under what situation journaling is preferred? Should be preferred.
I can give it a try, but I'm not sure if it's correct.
Thank you very much. Oh, by the way, before you say anything, Angela, this question is similar to a lot of questions in the operating system. There is really no there is no absolute correct answer. All right, so please go ahead, Angela.
Okay, cool. So for soft updates, we're taking snapshots, and it's probably like some more, regional, more like smaller file. For example, if we modify like a Word document or something like that, we just need a snapshot. But if, for example, we're trying to download a system, for example, we're trying to, download Anaconda to our, desktop or something, and suddenly if our power switch gets kicked off, how do we ensure that our download is still there after we turn the switch back on? And that's probably when we actually need like a journaling to ensure that the process, like that this big system update can be complete.
Okay, great. That's a great answer. I like your answer to consider situation like Conda or even a Docker kind of situation, which is we really need the whole thing to make it complete, to just naturally use a log-based file system like a journaling. Okay. Yes, other answer to other opinion on this issue? Yeah, I think Mithreya mentioned that it's the simpler design is a good thing for journaling. In fact, I think that is why Linux chose to go with journaling, because it's simple. It's a simple, you have a less bugs, and it's easier for you to maintain, to get extended. Okay, that's another from software development perspective. I want to just turn the table a little bit. Under what kind of situation you think that soft update has some advantage to be applied? What kind of situation do you think I would like to use soft update? Well, if nobody thinks that soft update has any situation that will be useful, then we should throw away soft update, right? It's complicated. You have to listen a few lecture from Felix, which has turned out to be useless anyway. Anyway, yeah, Sai, you want to say something?
Yeah. So if at all your data that so the thing is with journaling, it's all or nothing. It's binary. Either you lose everything or you get some or you get everything. So, but with soft update, for example, the application that you're working, if it is very important, then you won't end up losing everything. Like there can be some percentage with which you can work with.
Okay, you have some partial. Yeah.
Yeah.
Okay, that's a
partial.
good point. Yes, that's right. Any other advantage of soft update?
You have
It is
snapshots.
less. Sorry, go ahead.
Keep a long record of snapshots, useful in recovery tracing situations.
Sorry, I missed that one. Was that the comment from Mithreya or Claudia? I forgot. I couldn't catch. Can you say that again?
Yeah, so snapshots, it helps keep record of all changes that have been occurring between snapshots. So it keeps a record of all the past changes to the file system.
Yeah. Well,
It could help.
we actually, strictly speaking, when we talk about this soft update, background FSCK, and snapshot, we're really using snapshot for the purpose of background as FSCK only. Both journaling system and the soft update system, they both can do snapshot. In fact, they both, snapshot is kind of independent. It's necessary to support background FSCK, but journaling can also use snapshot. So that part is, so okay, one of the things I like to throw out here for you to consider that is actually potentially, just potentially, not deterministically, a advantage of soft update is about when you can use the file system. So if you think about this, with soft update, when the system crashed and when the system got reboot, when can I start using the file system? Almost immediately, because when the system back up, then essentially you just need to take a snapshot of that whole file system. And the thing is that you can just start using it without any trouble. Taking the snapshot, you do background FSCK. However, I never said this, but this is also important. In fact, you can start using the file system immediately, even without doing snapshot. See, what's the purpose of background FSCK and snapshot in soft update? Just doing garbage collection, right? Just try to collect those blocks that's should be free but hasn't been free. It's nothing changed to the integrity of the metadata. So if I really want to critical in some application, the real time for me to use my system and the file is very important, then soft update give me an edge because I know my file system is always consistent anytime. I can just use my file system the first second the system was reboot. In journaling, I cannot do that because journaling, remember, when the red may be in the middle of writing to the yellow and it crashed right there. So the thing is that in journaling, I always have to wait until the red is clear. The log has to be every piece of that has to be written down to the file system, the yellow, before I can start using the file system. It will be dangerous for me to use. So the thing is that this is referred to our earlier discussion. If I can maintain the red to be small, means that I don't actually accumulate lots of dirty pages. I will just basically spend maybe a few seconds to actually be able to clear the red to the yellow, and then I can use the system. So that's important. So in such application, especially if your red is getting too big, you should notice that you will not be able to use your file system, which means that the system is essentially unavailable until the whole red is being cleared. So that basically says that there is a fundamental difference is that journaling system, you need to spend time to clear the red, all or nothing, before you can use the system. For some application, even that small amount of delay is not tolerable. Then soft update might be a better solution for you to deal with. So I'm talking about real-time system. Some of the real-time system, critical mission system, because there is a bug. And then when you are actually doing some kind of critical mission real-time application, and suddenly the system crash. And soft update will guarantee the first moment the system is back up, you can use the system. That's the system availability in the responsiveness, okay? And I think that is very important for you to know the critical difference between those two, okay? Any question? Okay, as I remind you, today's lecture is very important for preparation for the midterm because I already made up the question, so I know where the question is coming from. Okay, so make sure when you prepare today's lecture, make sure you understand. Okay, all right. So I will close this, and so I can upload today's video to you as much as possible, as soon as possible. Okay.
Professor, I have some questions, not about the lecture, but about homework and midterm.
Okay. Can you give me a second? Let me turn off the recording first. Okay.
Okay.